In this video, we're going to be finding the exact value of expressions involving inverse trig functions, specifically those that look like these three here on the bottom. We have an inverse trig function with the trig function on the inside, and a trig function with the inverse trig function on the inside. All of these can be evaluated without a calculator, and will help unify many concepts of trigonometry all together in one problem. Here are some helpful things to remember and some concepts that we're going to use as we solve these problems. First, that an xy coordinate on the unit circle can translate to a cosine value and a sine value on the unit circle. We'll also be using the SOHCAHTOA method to help us determine the sine, cosine, and tangent of some triangles, as well as we'll be using the Pythagorean theorem to solve some triangles, and we'll need to re-express some angles that we find in terms of intervals that we need. We can do this by subtracting or adding 2π generally. Let's get started with our first example. We're going to evaluate the inverse sine of cosine 5π/6. We're going to start with the inside function, cosine of 5π/6. We can go to the unit circle, look up the value, and see that the cosine of this value is our x value, which is -√3/2. Now we can take -√3/2 and we'll put it inside the inverse sine function. We can use two pieces of information to help us find the angle that corresponds to this. First, that the inverse sine function gives us angles in quadrants 1 and quadrants 4. Second, we can look at the sine of the value we were given. Since it's negative, we know it should be in quadrant 4, which is where the negative sine values are located. Using these pieces of information, we can see that the angle we need is 5π/3. Instead of expressing it as 5π/3, we're going to express it as this negative angle right here. That way we stay within quadrants 1 and 4. We'll take 5π/3, we'll subtract 2π, and we'll get -π/3 as our final answer. Let's look at our next example. Evaluate the sine of the inverse cosine of -4/5. Like before, we're going to start with the inside function, the inverse cosine of -4/5. This is the same thing as saying the cosine of some angle is -4/5. We're going to start to draw a triangle based off this information. To help us draw the triangle correctly, let's identify which way to face our triangle and which quadrant to put it in an xy plane. First, we know that the inverse cosine gives us angles in both quadrants 1 and quadrants 2. So we're going to set that up with a triangle. Since -4/5 is negative, we're going to draw the triangle in quadrant 2 because that's where negative cosine values go. We're going to label our angle as theta, and we're going to put in the information that we know using the fact that -4/5 is a cosine, which is an adjacent over hypotenuse relationship. So in relation to our theta, we can put in a -4 on the adjacent side and a 5 on the hypotenuse. Remember that the hypotenuse is never negative, so that way we know that the -4 has to be negative. Using the Pythagorean theorem, we can fill in the last remaining spot as a 3, and now we're ready to take the sine of this angle. So we have the sine of the inverse cosine, but the inverse cosine represents just that angle theta. So now we can find the sine based off this same triangle. Sine is defined to be the opposite over the hypotenuse, which will be our 3/5, and that'll be it. Let's take a look at our last example, the cosine of the inverse cosecant of -1. To get started, we're going to look at the inside function again. The inverse cosecant of -1 represents some angle theta. Let's re-express this as the cosecant of theta is -1. Now, cosecants are kind of hard to deal with, so let's change it to a sine. We know the cosecant is the reciprocal of the sine, so 1 over sine is still -1. With a little bit of algebra, we can put sine in the numerator and see that it's still sine of theta is -1. Now we can go to the unit circle and we can find an angle that gives us a y value of -1, since y values associate with the sine values. Looking at the unit circle, the only place where this happens is this point right here. We have a sine value or a y value of -1. So we know theta should be 3π/2. Now we can take 3π/2 and we can put it inside the cosine function. The cosine gives us the x value of the angle. So we'll still go to 3π/2, but now we can look at the x value, which is 0. So we know our final answer will be 0. Here's a quick recap of the general process. On the first example, we evaluated the inside function using a unit circle. Then we took that value and put it in the outside function. This required us to find another angle, and we could narrow down which angle it was based off the range of the inverse trig function and the sine of the value that we had. We then needed to express this angle in the appropriate range of the trig function by adding or subtracting 2π. In the second example, we built a triangle in the appropriate quadrant and used the Pythagorean theorem to solve for the last side of the triangle. We didn't know the exact value of the angle in a triangle, but we were able to use the triangle to find a new trig relationship that the outside function asked for. In the last and third example, we found the exact value of the angle from the inside function by using a unit circle. We were then able to use this angle in the unit circle to evaluate the outside function. Some other resources to help you solve these kind of problems include the OpenStax textbook, the Pre-Calculus version 2E in section 6.3, and the Pre-Calculus textbook by Richard Wright. Both of these textbooks go through examples of these types of problems using similar but slightly different techniques, and they can help you understand the general principles. To help understand domain and range of inverse trig functions, I recommend the other two resources to help you find the guidelines and rules of knowing when to use which quadrants.